2355. You must be submitted. It's questions about something called generalized coordinates. We will stay here until we know what they are. Or of course you want to grade. Because of course it's marks. 40 questions, 40 marks. The idea of the pendulum. And at the end, we came upon the striking conclusion that in fact there are these things called forces of constraint, like the tension in a rod. They don't tell us anything new about the motion of the pendulum. Not something we don't already know, but often, in solving Newton's laws of motion, they provide us with a serious headache. These forces of constraint. Now I'm going to consider a few of them. When we have a pendulum, constrained to move in a circular path by a rod that is keeping it there, we say the tension in the rod is the force holding the ball at the bottom of the pendulum or the bob, or so it's often called, in a constant radius from the origin. But there are others. I've got a chalk box here. I'm going to place the talk box on the podium, or on here by the overhead projector. There it is. What are the forces on the talk box? Gravity pulling it downwards. Now I hear people saying something. Right, if gravity pulling it downwards, and the force is the mass times the acceleration. If gravity was the only thing there, what would happen? It would move downwards. Well, it ain't doing that. It's standing there on the overhead projector stand. It's not moving downwards. So something must be counteracting gravity. We call that the normal force. It acts vertically upwards or vertically away from the surface, normal to the surface of constraint. And it prevents objects from falling through other objects. Convenient, isn't it? Right? If physics dictated that when I walked into this podium I went right through it, well, it would be good for a spooky movie, but it wouldn't be good for this classroom. The point is that there is force or normal force that counteracts whatever force is pushing down on it. But notice again that in the case of normal force, it's a force we don't need to know. Yes, when solving Newton's laws, often we need to work out the normal force in order to know what the sum of the forces on the system is. The sum of the forces on the system is. To know what that sum is, we often have to work out what the normal force is. For instance, here is a classic example. You got a box sliding down a frictionless plane. Well, if you use Newton's equations of motion, you'd say the force acting on that is gravity. Oh, great, gravity goes down. Well, if that was the only force, the block would take its happy path straight downwards. But there's a plane there, and it's stopping it from moving. So we have to introduce a normal force. Normal force counteracting precisely that part of gravity which is moving into the plane, allowing the other part moving down the plane to take action. Right? So in order to solve for the motion of this using Newton's laws, not the conservation of energy arguments, which is Wellingham, but Newton's laws, we end up having to compute this guy, the normal force. Just like if we had been naive about the way we treated the simple pendulum, we would have had to have computed tension. So, it turns out, these forces of constraint are quite a headache. When I look at that picture, I know the box isn't going to fall through the plane. And does any of you honestly suspect that this thing is going to go through the surface? Or that I will walk through the podium? No. We know these things. There are constraints. There are constraints. I can't walk through the walls. I can lean against the wall and everything works out. I'm not going to suddenly be like, whoa! It's not going to happen. Forces constraints exist, but they effects of the obvious things. They're effects of the obvious things, not their values. So, what we want to do, our program, our mission statement in this course, is going to be to take mechanics and phrase it in a way that we don't have to worry about this. That we don't have to worry about any of this. So that we can forget about the value of the tension in the rod, about the value of the normal force keeping things up, about the things that keep rigid bodies together. I mean, if I'm actually considering this chalk box very carefully, well, not the chalk box with this stuff inside, I mean, consider the chalk. If I consider the chalk very carefully, well, what's the chalk made up of? Atoms, particles, molecules of chalk. Right? A whole bunch of little things. Well, if I have to model these things mechanically, I have to model millions of particles, really. But I don't actually have to model millions of particles, surely. I know that they're all sticking together. That's a good thing, right? They tend to stick together and remain in this thing I call chalk. And that's called the rigid body constraint. There's electrostatic forces holding these things together. Constraints. A whole bunch of them. Millions of them. I hate them. Constraints. Right, so the point is, we have to deal with them when they come up. We have to find a way to elegantly express constraints without dealing with forces. That is our program. That is our mission. We will not sleep until we have achieved it. Do I have your consent? Right. So that's the important thing to think about. It's a concept that baffles a lot of the best scientists as they consider these equations, is that the forces of constraint tend to be things that we can forget about. Specifically, when the constraints are things like walls or rods, and we know that this thing is going to slide down, it's not going to go through the block. Almost it's too obvious to state. And yet to solve Newton's equation of motion, we have to bring up the normal force and all these other funny things. So I'm going to just quickly consider the other way of dealing with constraints, right? We've looked at the forces of constraint, normal force, tension. What about the equations of constraint? Generally, a constraint comes along with some equation that says the system moves in this way. Let's have a look at how those things move. For the inclined plane, if we have an x-axis there and a y-axis there, the constraint says the object does not go through the block. It instead slides slowly down. It basically says that the object is not allowed to move off of this line. Right? Well, what is this line? This is theta. That's the line through the origin with a gradient of theta. Gradient, right, is given by y over x for a theta triangle, tan theta. Right? So that is an equation of constraint for the system. Right? We can consider a different coordinate system. Maybe we don't like tans and we think that that's a little bit ugly. I mean, we can rewrite this, of course. Y is equal to x tan theta. Or if we generally don't like tangent functions, we can even think of tan as a sine over a cos and write y cos theta minus x sine theta equals 0. Alright, we'll see why I want to write it like this in a minute. An alternative, of course, is to think about changing my coordinate system. If instead of writing it with coordinates x and y, as I have stipulated them, if I put my y coordinate going up like this, and my x coordinate going down the plane, and then I put my box over here, well, this chap is simply not allowed to go up and down, is he? So the constraint in this situation is very easy. But this indicates another thing that will become clearer and clearer to us as the course goes by. Our choice of coordinate system often makes a very big difference to the difficulty of the problem. In these coordinates, the constraint was y cos theta minus x sine theta is 0. In these coordinates, the constraint was y is equal to 0. Right? Not easier. The thing moves just along the x-axis, right? Y is equal to 0. There's another kind of constraint. What if I allowed the box to jump off the surface, but it's still really not allowed to go below the plane? Well, then I could just have written it as y is greater than or equal to 0. There are a couple of other situations that I can depict. The pendulum, of course, we've seen this one, and we've actually written out the equation of constraint. The pendulum is not allowed, if this is a steel rod or something, it doesn't change its length as it swings. So the pendulum tends to move at a constrained distance of L from the origin, right? So if we choose our coordinate system to be x, y, as we've been doing, then the equation of constraint is x squared plus y squared is equal to L squared. Alternatively, if we choose polar coordinates, which we also did earlier, the equation of constraint is simply r equals L. And now you can see how our choice of coordinates dictates how easy or difficult it is to write down the equation of constraint. If we had chosen another system, let's say I've got a wheel. I couldn't find an old tractor wheel lying around, so I rolled it up here. But I'll just use a dustbin lid. It's unhygienic, but it'll work. Don't shake my hand after this. Right. It's rolling, it's not slipping. Right? It's rolling along the ground. I ain't lifting it, sorry guys. I have standards, even I have standards. Right, so if it's rolling along the ground without slipping, that's different from if I make it slide, right? There's a constraint involved in the fact that this wheel is rolling without slipping. That constraint is expressed how? Well, I've got some wheel rolling along the ground, right? And if it doesn't slip, we can say it starts out with some point on the ground. And as it rolls, that point will, rotate along the wheel. You kind of visualize that. When it's over here, it's changed shape. It gets to this point, maybe it's rolled to there, right? So it's rolled around. When it gets here, maybe it's rolled all the way back to there again. So you can see how the point is rolling, right? But there's a constraint associated with this rolling motion. What is that constraint? It says that the distance traveled along the edge of the circle, right, is the same as the distance traveled here, right? Does that kind of make sense to you? No. As I roll a circle along, I can derive this mathematically. I was hoping that it would look intuitively obvious, but I may have to get down and derive this mathematically. But as I roll a circle along the ground, if I'm not slipping it, I expect that the distance I cover along the circle that is rolled along the ground is the same as the distance that is covered on the ground. right? Let's derive that, right? Let's derive this result. Then in fact, what have I said? I've said that the distance is moved on the x-axis is equal to r times the distance that the angle has moved. Right? R is the radius of the and r theta will give me the distance of this arc. So I'm relating the angle of the thing to the distance that it's moved. Because moving and rolling at the same time. I can look at this mathematically. Mathematically, when I say something is rolling without slipping, it means that the tip, the point in contact with the ground of the wheel, is never moving at all. It's stationary. That's what rolling without slipping means. It means that static friction is driving the system. Those of you who took the first quiz will at least have seen this concept written down before when you got the wrong answer to the true and false question. Essentially, when something is rolling, its tip, the point on the ground, doesn't move. Because if it did move, it would have to slide. Right? It just rolls over to the next point. And the point in the ground itself is always stationary. How do we write that mathematically? Well, this disc is moving, the center is moving with a velocity v. And this point here, which I require at all times to be stationary by my no slipping constraint, is moving with what velocity? Well, the first part of the velocity is v, because the whole wheel is moving at a velocity v. Plus, there's another part of the velocity, the angular velocity due to the rotation of the wheel. And the angular velocity is always given by r theta dot. And in this case, it's going that way, minus r theta dot. Right, and v in this case, I can just think of as x dot, can't I? The rate at which the wheel is translating through the plane, the derivative of its x coordinate. It's x velocity, x dot. So this thing here, I require to be 0. This is the velocity of the tip. And if I require that to be 0, well, presto, I can integrate both sides of that equation, can't I? So, let me integrate. The integral of x dot minus r theta dot, let me include bounds from 0 to t. Right? dt. And here I'm being very lax in notation. I've got a t here and a t here, which you should never do. But if I put an s here, I confuse you more. So I'd rather be incorrect whilst not confusing you as much than correct whilst confusing you. So here we have, so what's the integral of x dot? So it's the integral from 0 to t of dx dt dt plus the integral from 0 to t of, well, there's an r that comes out, it's important, d theta dt dt. This is the fundamental theorem of calculus. These things are easy to figure out, right? We can integrate these out. And this is equal to the integral from 0 to t. Well, this was equal to 0, so this is equal to the integral of 0 dt. Right. Well, that's great, because fundamental theorem of calculus is telling us everything we need to know. That first integral becomes x minus x0, x minus where x started, plus r times. The second integral becomes theta minus theta 0, theta minus where theta started, is equal to the integral on the other side. Yeah? Yes, correct. You get a star. Very good. It's going to be a minus. Because there was a minus r up there. There should be a minus here too. Right. Is equal to what? The integral from 0 to t of 0. naught because it's a constant at two different points subtracted from each other. Right. Well, let's assume that I start at the origin so that x naught is naught. And let's assume that I set my angle so that when I begin my rolling action, theta is naught as well. Then I have x minus r theta 0. So x is r theta, and indeed I related x to r theta, just like the intuitive argument did, but now mathematically correct. So the distance that we travel along the ground is the same as the distance that has been rolled out on the edge of the circle, as the circle rolls in one dimension. And that's another constraint. It's an equation of constraint. What is the force of constraint here? Remember that in the case of a thing lying on the ground, me standing here, it's normal force. In case of the pendulum, it's tension. What is it here? Kinetic friction. Static friction. Right, so yes, good. Friction is correct. Static friction is that. Because it's the friction that's keeping the tip from sliding. It's keeping the tip from sliding, so it's causing it always to be stationary. And it's causing, therefore, the rolling action. When you push a wheel, and the wheel rotates instead of sliding along, it's because static friction is constraining the system to rotating motion. So it is the force of constraint in that instance. So I've got a bunch of constraints written up here on the board, and I want to ask a certain question of them. I want to ask, which of these constraints is holonomic? And holonomic is a Greek word. And it really comes from holos and nomos. And holos means entire. And that's actually nomi means law. So holonomic means entire law. Well, which of these are entire laws? I don't know. Let me define it mathematically for you. Holonomic. Someone's about to violate the normal force upstairs. Holonomic, by definition, is a constraint that can be written as some function of the coordinates and time, but not the velocities equals to 0. Right, so some function of my coordinates, x1 to xn, and time, but not the velocities, is equal to 0. And these are very special constraints. Because when I can write a constraint out like this, it's always possible to do what I did with the pendulum, to ignore some part of the equation of motion, to ignore some part of the system, to simplify my problem, to ignore the constraints, ultimately. So holonomic constraints are the important ones. These are the things that we want to look for in our systems. Are they obeying this kind of constraint? Can we reduce the number of parameters required to describe the system, the degrees of freedom of the system? Can we do that? And we can do it if it's holonomic. So let's look at each of these constraints, which I've written up on the board, and let's ask, is it holonomic? This one. Who says no? Who says yes? What's the question? You can't ask what's the question after a poll. So the question is this constraint, this equation, holonomic? Is it a function of the coordinates, but not the velocities, and possibly of time, equals to 0? Is that the form of the constraint? Yes. Come on, guys. Yes. Yes. Let me hear you. Right up here, do a better job. This is holonomic. Because here is 1, here is x. These are constants because my theta is a constant, right? So these are holonomic constraints. They reduce the number of degrees of freedom. They reduce the intrinsic dimensionality of the problem. Because, why? Ultimately, we only have to think of motion along a line. There is a function in mathematics, formula, theorem, called the implicit function theorem. Have you heard of it? Yes. Is anybody here brave enough? Tell me what it is. We are mathematicians. You better not shy away from something like that.
Done real analysis that the implicit function theorem something to do with differentiation of particular.
It's not the inverse function theorem. Implicit function theorem. The implicit function theorem is very simple. It says if I can write f of x1, x2 to xn and maybe some other parameter equals to 0, right? If I can do that, and if f is a continuous transformation function, or continuous function, this guy's continuous, and f is continuous, 1, then I can rearrange this, locally at least, always, no matter what the form of the function is, to write x1 as some other function, h, of the others. Okay, so basically what the implicit function theorem tells us is that if I've got some holonomic constraint, like this, then I can rewrite one of my parameters, one of my coordinates, in terms of the others. Okay, then I can rewrite x1 as some function of x2, x3, etc. And indeed, I can do it over here. Let's rewrite y as a function of x. Go up one step. There it is. So, I've got some holonomic constraint. I can rearrange it, guaranteed by the implicit function theorem, into this form. Y as a function of x. I only need to consider x as it changes, and y will be given to me by the value of x. Because the instant I know what x is, I multiply by tan theta, and voila, I've got y. Okay. I can do the same thing in different coordinates, although I erased it. But if I did the same thing in different coordinates, these coordinates, where I had y equals to 0, was still holonomic. It was in a different coordinate system, but it was still holonomic. Some function of x and y is 0, y. Function of x and y. Right? And what about the pendulum? Is the pendulum a holonomic constraint? Yes. Yes, it is. Because I can write x squared plus y squared minus l squared equals naught. Function of x, y, but not of x dot, not of y dot, equals to 0. R equals L. R minus L equals naught. Holonomic. Correct. I can reduce the number of degrees of freedom. Once I know theta, I know the entire position of the rod, of the pendulum. I just work out R plus theta and R sine theta. Once I know theta, once I know x, I can work out y. Once I know the x displacement, I can work out the height.
Okay, when can't you do that? Because so far with each of the examples, you've been able to take one term across and have your entire term equal to 0. So when can't you do that?
So, for instance, in the x squared plus y squared equals L squared case, I can take x across and I can write, not entirely obvious this one, I'll show you why. I can write x is equal to the square root of L squared minus y squared, right? That's my taking across. But actually, this only applies locally, right? It'll work for both positive and negative y, won't it? So there's two different values of y that will give me the same answer there. So there's a little bit of, and plus this is plus or minus as well. So it actually is two